Absolute value functions are functions that are what we call piecewise linear functions. The definition of an absolute value function looks a little strange at first. The absolute value of x is equal to negative x if x is less than 0, and x if x is positive. It might be easier to think of that first part of that definition as the absolute value of x is the opposite of x if x is negative. If x is negative 3, the opposite of negative 3 is positive 3. Most people remember the absolute value function as it makes something positive. One use of the absolute value function is to determine when the distance between two numbers is within a given range. So they want to describe all values of x that are within 3 units of 7. So we want numbers that are close to 7. They're no more than 3 units away from 7. So the number 6 is within 3 units of 7. The number 9 is within 3 units of 7. Our model for this would be the absolute value of x subtract 7 is less than or equal to 3. So that the distance between x and 3 is less than, the distance between x and 7, the difference between x and 7 is less than 3 units, is how that sentence would translate into algebra. If we look at this on a number line, I find this helpful. If we have the number 7, we want the distance for our unknown variable x to be less than or equal to 3. So from 7, we might go 3 units below 7, or 3 units above 7. That would drop us as low as the number 4 and as high as the number 10. So any number between 4 and 10 is within 3 units of 7. The graph of the absolute value function, absolute value of x, is 2 linear lines. A straight line y equals x, as long as x is greater than or equal to 0. And a line negative x, so through the origin with a slope of negative 1, as long as the inputs, the x values, are less than 0. So we get that V-shaped graph. We can do translations of that V-shaped graph. This particular one has been shifted left 2 units and down 1 unit. It still has the same shape as a basic graph. It's got that slope of 1. As you can see, we're going up 1, over 1, up 1, over 1. So there haven't been any stretches. And it's still a V pointing up, so there has not been any reflections. And so we need to take our basic absolute value of x and do a translation left 2 units and down 1 unit. So x plus 2 inside the absolute value of x modifies the input, and that would shift us left 2 units. And then a subtract 1 would shift the function down 1 unit. And then we can verify this in a graphing utility. Another one, this one we can see has a reflection over the x-axis, and a little more subtle is it's also been stretched. So looking at the graph, instead of going over 1, down 1, it's going down 2. And so there's been a stretch by a factor of 2. We can also see it's been shifted right 1 and down 1. So let's list out the translation. It's been moved right 1. It's been moved down 1. It's been reflected over the x-axis. And it's got a vertical stretch of 2 units. The slope is now twice what it was before. And so that would give us the function negative 2. The negative would take care of our reflection. The 2 would take care of our stretch. Let's see, x subtract 1. For the shifting it right 1, and then subtract 1 to shift it down 1. And that would be our new function, which we can verify on a graphing utility. Okay, in general, graph of an absolute value function may have none, one, or two horizontal intercepts, just like a quadratic function may have none, one, or two horizontal intercepts. A absolute value function that's been shifted, say, right and up, but not reflected, would look something like this, and it would have no horizontal intercepts, no x-intercepts. This particular absolute value function would have two horizontal intercepts, and that one would have one horizontal intercept. So when we're solving equations, we may be coming up with none, one, or two solutions to an absolute value equations, as we do with our quadratic equations. Also, these are not one-to-one functions, so they don't have inverses. To solve an absolute value equation, remember the basic definition is that it's either equal to the opposite of x or x itself. So if we have the absolute value of 2x subtract 3 equals 5, the input, the 2x subtract 3, is either going to be equal to 5 or it could be equal to negative 5, and either way its absolute value would be 5. So we can solve each of these equations separately, and we're going to come up with two solutions. This next example, the absolute value of 4x subtract 7 equals negative 2, is a bit of a trick question, because an absolute value is always equal to a positive value. So this one would have no solution. Our third example here, we need to do a little algebra before we can apply our definition for the absolute value. What I want to do is isolate the absolute value. So first I'll subtract the 4, and then I can divide by the 5. So I'm trying to peel off everything that's not inside the absolute value. Once I've got the absolute value isolated and equal to 4, I can now apply my definition, split the problem into two separate problems. Each half I can solve, and I'll come up with two solutions. X equals 3 and x equals 11, and then we should take the time to substitute all these back into the original problem and verify that they are in fact the correct solutions. Now, to solve an absolute value inequality, there's two approaches you can use, graphing and test values. I like the graphing method best myself because I like pictures. So you can try both, see what you like. We'll do the graphing method here first. So I'm going to start off looking at absolute value of x subtract 7 less than or equal to 3. Absolute value of x subtract 7, the graph of that would have its vertex at the 7. No stretching, no reflection, so I'm going up the slope of positive 1 to the right from that vertex, a slope of negative 1 left of the vertex. And what I'm interested in is when that absolute value function is smaller than 3. Now if I locate 3 here on the vertical axis, what I'm looking for are values of x so that the function is smaller than 3, below that red line. And that's going to correspond to this interval here, between 4 and 10, which is what we had when we originally looked at the problem. We were looking for this original problem we were describing, when is the distance from 7 less than or equal to 3, and that was between the numbers 4 and 10. So our solution to this would be or using interval notation, the interval from 4 to 10, including the 4 and the 10. The other method we can use to solve the same problem with the test values is we first take the inequality, set it equal to 3, and get the two solutions to that equation. So are what we call critical values. These are going to be where the value changes from being less than 3 to greater than 3. And I'm going to take these two values, put them on a number line. When they're on the number line, that divides the world of numbers into 3 groups. And I can pick a test value within any of these numbers. So a number smaller than 4 would be, say, 0, or 1, or negative 23. Pick any number smaller than 4. Pick any number between 4 and 10. I like 5. It's a nice number. And then I want a number in this last interval greater than 10. So maybe the number 15. And what I'm going to do is take each of these red numbers, these test values, take it to my original inequality, and see whether or not it makes the original inequality true. Does x subtract 7, is that less than 3? If I use x equals 0, I get 0 subtract 7 less or equal to 3. True or false? Well, the absolute value of 0 subtract 7 is 7. 7 is not less than 3. So the numbers in the interval represented by x equals 0 aren't going to satisfy the inequality. If I let x equal 5, 5 subtract 7 is negative 2. The absolute value of negative 2 is 2, and that is smaller than 3. So the numbers in this test interval between 4 and 10 are all going to work. And then taking my last test value, my 15, to check the third part, my third interval, is that going to be true? 15 subtract 7 is 8. The absolute value of 8 is not smaller than 3. So this interval does not work. So I want the numbers between 4 and 10 because they make my original inequality a true inequality. Those are the solutions to the inequality.